All right, section 2.4.2 is what we were working on last time with prime and composite numbers. And I think that we had just talked about the fundamental theorem of arithmetic. Does that look right? 412? Back on the previous page from where you guys are looking right now. This one, nope. I don't think I'm far enough. It was. Where am I finding it? 414. Why am I finding it? Okay, I was wanting to reference the last slide, but I don't find it. That's okay. Let me just talk in general about what it was. The last slide that we had looked at, we talked about the fact that when we divide things, they occur in pairs, right? When we divide a number, if it's divisible by 2, it means it's divisible by itself divided by 2 as well. These numbers occur in pairs. So we looked at the number 24. If 24 is divisible by 3, 24 is also divisible by 24 divided by 3, which was 8. These numbers occur in pairs. The reason that that's important is because that comes into play when we take a look at theorem 415. When we have a composite number, and we are looking for prime factors, we're trying to decide, is the number really prime or is it composite? The number that we can, there's a place where we can stop looking for factors. Like the example you were doing, Taylor, when you were with the number 209, if you had not found the numbers to be divisible by 19, how far would you have to go? How far do we need coming to test all these numbers before we say, you know what, it's prime, it doesn't divide by anything? Do we test everything smaller than it, or is there a place where we can stop just short? So this theorem actually says that if you do have a composite number, right, a number that actually divides by something besides itself from 1, then it will have a prime factor p, where p squared is less than or equal to n. And what this tells you is where you can stop looking for factors. I'm not getting my pens on right now. Excellent. What's that? Like here, you mean? That shouldn't affect that though, because you see how this is blinking? Because this button is blinking is why it's not letting me write on my screen. I wonder if I put these in the wrong direction. Let's try this. I haven't had smart word problems in quite some time. I guess I was due. All right, let's talk about this. So write down what I say even though it's not on the screen. Okay, so here's the deal. You can stop looking for prime factors once you have reached the number that is the square root of the number you're working on. Okay? So once you have a number, let's say for instance your original number was 342. You want to know, is it prime? Well, 343, let's put that one since maybe 342 is not already. 343, you can stop checking to see is the number prime or composite, that is, stop trying to divide it out once you reach the square root of 343. It gives you sort of the upper end of where you have to worry about values on. Okay? And if you reach that value, whatever the square root of 343 is, and you haven't been able to divide it by anything else already, then that means that the number 343 is a prime number. Okay? That's what these two slides here tell you. So we're going to do an example of one, although I guess I'm going to be writing on the chalkboard since I can't write on the smartboard today. It says, what is the greatest prime that you must consider to test whether 963 is a prime? So what did I say that we needed to do? Find the square root. So, grab your calculator out. I'm not expecting you to do square roots in your head from today. And I want to know, roughly, I mean, it usually isn't exact. Usually it's got some decimals and stuff and so forth. What is the square root of 963? What is your calculator give you for the square root of 963? What's it say? Andrew, what did you say? 31.2. 31.2. 31 point something. All right, so the closest value to that would be roughly 31, right? And 31 is a prime number, agreed? Yeah, there's not any numbers that divide 31. So we could actually stop testing numbers. If we were looking at this, we could stop testing at 31. Now, we would have found it long before that because 963 is actually goes by 3, right? Yeah, because the 9, the 6, and 3 each individually work. But we could actually use that for any value that we're doing instead. There's nothing special about 963. So we find the square root of that value, and then we can test all prime numbers beneath that. If we don't find any that divide the number, then the number itself is prime. That's a really nice feature. Because 963 is pretty big. To think that I only have to test numbers until I get to 31 to know, that's cutting down a lot of ground, isn't it? It really is. We talked about example 3 last time. I think I did sort of an aside. I said that was a bonus or something like that. You didn't even know you were going to get that today. I didn't know I was going to tell it to you. Number 3, example 3 tells you why that happened, or kind of further indicates that information. It says, show that if the number 1 were considered a prime, then every number would have more than one prime factorization. And we did that. I don't remember what the example was that we did it on. Can you guys tell me what was it? Was it 4 times 3 was it 12? I think it was the number 12 that I did it with. So we had the number 12. And we talked about this, that prime factorization for this, as we understand it, would be 2 times 2 times 3. And if the number 1 were a prime factor, then we could also say that this is 2 times 2 times 3 times 1. Or even worse, 2 times 2 times 3 times 1 times 1. And then I have all of a sudden multiple ways of writing a prime factorization for a number. So the number 1, the value of number 1 being a prime number is a very helpful thing that it is not. If it were a prime number, that is, if that's how we classified it, we would not have a unique representation for prime factorization. It wouldn't be one and only one prime factorization for every number. All right, let's take a look at an application of divisibility. So this is a true application of how we think about divisibility. It says, Mr. Arbor, adequately named, wants to plant apple trees in a rectangular array. Okay, so he wants sort of, we talked about arrays, right? He wants a length and a width, and they're going to be all apple trees. They're going to be nice and evenly spaced. He's probably a little OCD like I am. Right? So he's going to put them in a rectangular array, and he has 36 of them to plant. So the question is, find all possible numbers of rows if each row is to have the same number of trees. So we've got an array. We've got a grid in how he's doing this. So what's one option that he could have for his array of trees? What? 4 and 9. So you could have 4 trees and 9 rows, or the other way around, right? You could have 9 trees and 4 rows. So he has 4 wide, 9 long, in other words, or vice versa. So if you have 4 and 9, what else could he have? 12 and 3. So 12 trees, 3 rows. What else could he have? 2 and 18. You could have 2 trees and 18 rows, or you can think about it backwards, right? 2 rows with 18 trees in each of them, the 2 by 18 grid. What else could you have? 6 and 6. 6 trees, 6 rows. I know that's a square, but you know a square is a rectangle. It's all okay, I promise. A square really is a rectangle, it's all right. And one other option. You could just have 1 row. So you could have, we'll say you could have 36 trees, 1 row, or you could say he has 1 tree in each row. There's 36 rows. It's a little awkward to say it that way, but you could say it that way. So what we're doing is we're looking for all of the pairs of numbers that multiply 36, right? That's all you just did. That's an application of divisibility. In your mind, you're asking yourself, what numbers divide 36? And while we didn't sort of write them down in order, the way that it makes sense to sort of think about them so that you don't miss anything is to write them down in order. You can start with 1, and then you can go up from there, 1 and 36. The next highest value would be 2, so that would be 2 and 18. The next highest value, divisibility, would be 3, 3 and 12. You get to 4. 4 gives you 4 and 9, right? 5 doesn't work. 6 does. So we get 6 and 6. And then we've run out of options because anything any bigger than 6 is already represented, that divides it is already represented on the right-hand side. So these are my lists of numbers that are actually factors of the number 36. Any questions on that one? That's an application of divisibility. Let's take a look at the last one. Bob says that to check whether a number is prime, he just uses the divisibility rules he knows for 2, 3, 4, 5, 6, 8, 10. He says if the number is not divisible by these numbers, then it isn't prime. How do you respond? What's going to happen if this is all we do? Let's try this. Could that work? Is it possible that he checks these and it actually turns out that that's sufficient for a particular solution? Sure, it could work. Will it always work? No. Can you give me an example of one that wouldn't? What's that? 49. I think 49 because it's got the 7 in there. That's true. 49 would work because we didn't have a divisibility test for 7. That's a good example. What else can we have? What's that? Yeah, that one will actually be okay. Is that 121? So what's wrong with 121? Right? So if you used 121, that would be divisible by 11, but that number is not in this on the list of numbers. And in fact, if we took 11 times anything that's prime and bigger, it would work, right? 11 times 13, that value, whatever it is, would give me a value that doesn't divide by any of these, but it does divide by something. It is a composite number. So there's nothing wrong with his list, it's just that it's incomplete, right? And not only that, but it sort of misses 7 entirely, as Carly pointed out with number 49. If numbers divisible by 49, we got problems. If you did 77, that would work too, because that's using your 11 and your 7 to cause problems, both of those. Okay? Any questions on that one? All right.